Hi everyone, my name is Li Hao. Today we're going to do Advent of Code 2020. So Advent of Code 2020 is a series of programming challenges on the Advent calendar, where every day we have one programming challenge. Sorry for my bad grammar. One programming challenge, and on that challenge we have part 1 and part 2. So solving each of the part gave us 1 gold star. So at the end of the programming challenge, at the end of the calendar, we'll get 50 gold stars, which is the aim of the this challenge, right? So today we're going to attempt day 14, which means that if this is the first time you are watching this video, you are losing out. Day 1 to day 14, day 1 to day 13, and you can watch all of them on the link over this corner. Okay? So let's dive into day 14. So we have the calendar over here and we're going to do day 14. So day 14, docking data. As your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that a seaport's computer system uses a very strange bit mask system in its initialization program. Although you don't have the correct decoded chip handy, you can emulate it in software. The initialization program, which is the puzzle input, can either update bit mask or write a value to memory. Values and memory addresses are both in the 36 bits unsigned integer. For example, ignoring bit mask for a moment, this would write the value 11 to the memory address 8. But the bit mask is always given as a string of 36 bits, written with the most significant bit on the left and the least significant bit on the right. So the current bit mask is applied to values immediately before they are written to memory. A 0 or 1 overrides the corresponding bits in the value, while the X leaves the bit in the value unchanged. So considering this following program, this will be the mask, and we are setting memory address 8 equals to 11. What happens is that so the decimal of 11 will be like this, 1011. So this bit mask specify overrides 2 bits in every written values. So the program attempts to write the value 11, right, expanding to individual bits. So X is ignored, but whatever is 1 will have to be 1. So it will override this value as 0, override this value as 1, and leave the rest unchanged. So when you write decimal 11, you're actually writing 10010001 in binary, which in decimal is 73. So because of the mask, value to 73 is written to the memory address 8 instead. And then tries to write 101 to address 7. So 101, which is in binary. So after overrides this value as 1 and this value as 0, we ended up with 1100101, which is still the decimal in decimal, which is 101. Right? So this mask has no effect. The bit is already has the value the mask tries to set. So 64 is previously written a value 8 instead. So if you're writing 0, you write 64 instead. To initialize a ferry's docking program, you need the sum of all values left in the memory after the initialization program completes. The entire 36-bit address space begins initialized to the value as 0. Okay, and 0, I believe it's 0, which is empty, not decimal in 64. Okay, and 2 values in memory are not 0. So in the above example, we have written 101 and 64 to the address 8. This overrides the first memory, right? So only address 7 and address 8 is written. And we have value of 101 and 64, producing a sum of 165. So execute the initialization program, and what is the sum of all the values left in the memory after it completes? Okay, so let's try to get our puzzle input. Let's save this into input.txt. What we're going to do is we're going to copy this file to day 14. I'm going to code day 14 as well. Okay, so first thing first is to import fs and read the file content. Day 14.txt. Alright, so let's take a look at the contents of the data of the file. You have a mask and then memory assignment and then mask and then memory assignments and so on and so forth. Okay, so there are two kinds of line inputs. One is the mask, one is the memory, right? So I think first thing is we have a mask and we have a memory. We're gonna have memory. So I'm going to use a map instead of array of 2 power of 36 number of zeros, right? So if it's 0, we don't set it into a map, just ignore it. So we only keep track of values that is assigned, and we can add up all of them to get the sum. So this saves us some memory space that we don't need to record content address that is with no value or 0 value, right? So the next thing is we're gonna go look through the okay, so let's see, content.split by new line, and then we're gonna for each line what we'll do is we are going to test whether it starts with mask, right? If line starts with mask, then probably it is this mask input, right? As I said earlier, I love to use regex, so we can use regex to parse this thing out, and we can actually reuse the regex to see whether it matches this line of content. If it matches, then and then we map it out with regex, right? So we have two kind of regex. One is the mask regex, which starts with mask space equals space, and then this is the content that we want to get out of it. And if you want to be stricter, you can even say x0 and 1, right? And we can have and then the next one is the memory assignment line, which memory regex. I'm gonna name it this way, and how it looks like we'll have two different match groups, which is the numbers, which contains a lot of digits, and to escape this square brackets as well, because square brackets in regex means another thing, right? So if mask regex dot test if this line matches the mask regex, which means it's the mask line, then we will line dot match mask regex, and actually we have one capturing group, which is the mask value, right? So this and the mask value, or I will say the mask string, then I will set mask equals to create mask string. Okay, so this will create a mask for us, which we can use it later on. Then next thing is that else, then the next line we are gonna see is most likely the memory regex line. So we have two matching group. So the first one is the memory address value, and this next one will be the value, right? So okay, so I'm gonna set memory dot set number of address value, and then this value would be the we're gonna use the mask dot mask. So mask will have a method mask called mask, which we will define it later as well, and then we'll pass it with a number value, right? And then at the end of it, we will go through the content or the values within the map. So value of memory.values, we'll get the sum of it. Sum equals 0, sum plus equals value, and that will be the answer value, right? And now we need to define the create mask. So create mask will give us a string, the mask string, right? That names it better, mask string, and it returns an object with a method called mask, right, which takes in a number, which is like a value, right? Okay. So now with this mask string, what we are going to do is that we are going to split the string. Mask array equals mask string dot split. Okay, so it will split this whole thing into individual bits, where it's 1, 0, or X. Okay, and when we are doing a masking, what we're gonna do is that we are going to loop through this list, and then if it's 1, we'll set that bit as 1. If it's 0, we'll set that bit as 0. If it's X, then we'll use the whatever bit that is from the value that we are passing in. Okay. So you might ask me, like, why am I using a mask array over here instead of, say, using bitwise operator? Well, we can't really use a bitwise operator over here in JavaScript because bitwise operator operates on a 32-bit number, which is slightly above or beyond what we are handling over here, which is 36-bit numbers, right? There's 36 bits over here. Okay, so we can't use a bitwise operator, and we have to handle it ourselves. So we can loop through the 36 bits, right? I less than 36, I plus plus. So we're gonna set this number, return value equals to 0 at first. So we're gonna use this to loop through the mask string, right? So so we start from 0 to 36, which is 0 to 36 over here, but actually this is the so-called 35th bit shifted to it's 2 to the power 35, right? I think I get that right? So if it's say 1, okay, so this is like, if this is 5-bit number, then this is 2 power 0, power 1, power 2, power 3, power 4, 2 to the power 4, right? So if it's 36, then it will be 2 to the power of 35, as 5-bit will be 2 to the power 4, right? So I'm gonna do here is that we're gonna have the bit position starts with 35, and then as we loop through, we're gonna decrease it in state. And so mask array, if it's okay, so there's, how about use a switch case instead? Mask array I. So there's 3 different kind of scenario that we can have for the mask array, right? So if it's X, then we do nothing. Or rather, we're gonna apply the values bit. If it's 1, then set bit as 1. And if it's 0, then we're gonna set bit as 0. Okay, so if it's an X, what we're gonna do is we are going to say, okay, over here we're gonna get the we're gonna get the binary representation of the number, and then let's see what's a better, I feel like this is a bit slightly a bit complicated, because while I'm thinking through this, I find that there's a slightly easier way of writing this. Okay, so the first thing is get the toString. Yeah. Wait, is it toString? Let's try. Note a equals to 5, a toString. Yeah. toString will give us a string representation of the number, and we can pass a base value. If it's 2, then it will be a binary representation. So what I'm gonna do here is that binary value equals to value.toString 2, and then probably we're gonna pad it with zeros in the front, right? So let's say this is let's and then binary value equals to padding of 0, repeat binary value dot length. It should be 36 characters, right? So 36 minus the length will be the number of zeros that we're gonna pad binary value, right? So this is like a left padding of adding zeros on the left side. Once we get this, we can actually combine these two strings, right? So the result string, the result binary value 0. Okay, and then we're gonna loop through let I equals 0, I less than 36, I plus plus. Same thing, switch mass array of I, case of X. Then we're gonna use the use this binary value of I, right? Break. If it's 0, then we're gonna add 0, right? Break. And if it's 1, we're gonna add 1 as well. So if we combine these two cases, it's actually result plus equals to mass array of I. And that's all the case that we need to handle. And once we are done with this, result binary value, once we are done with this, we can actually return this value we can actually parse it into number again. Result binary value, comma of 2, radix of 2. Right, and let's clean this up, and let's try exit. Let's run this. I don't think it's day 22, day 14.js. Okay, something is callback must be a function. Read file sync. Okay, typo over here, and we fix that, and value is not defined. Well, it should be the sum. Okay, continue, clear this, and run this again. Okay, we have a number, and hopefully it's the answer. So we're gonna try it in over here, and let's try. Yes, that's a right answer, man. Okay, we are one step closer to getting a second star. So let's go to part 2. So for some reason, the CPOT's computer system still can't communicate with your friend's talking program. It must be using a version 2 of the decoder chip. Well, a version 2 decoder chip doesn't modify the values being written at all. What? Instead, it acts as a memory address decoder. Immediately before a value is written on memory, each bit in the binary mask modifies corresponding bits of the destination memory address in the following way. Bit mask is 0, corresponding memory bit is unchanged. Bit mask is 1, corresponding memory bit is overwritten with 1. Bit mask is X, memory bit is floating. So a floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means floating bits will take on all possible values, potentially causing memory address to be written all at once. Okay, so for example, in this example, if you're writing to memory address 42, and 42 in binary is 101010, with the mask, you get 1, you overwrite with 1, 0, you leave it unchanged, 0 unchanged, 1, you map it to 1. So you end up with x1101x, which means that actually 4 bits are overwritten. So x stands for x can be anything, right? So x can be, so there's 2x, which means there's 0001, 1011 of different combination of the x value. So actually writing this value to 4 memory addresses. 4 memory addresses, right? 26, 27, 59, 58, 59. The next one is you're gonna write to memory address of 26, because you set a different mask. You have 3 x's now, and this ends up with 8 different kind of floating combinations of it. So you will add up, you will change another 8 more memory addresses. So now you have the new sum, which is 208. Right, so we're gonna change the code and we're gonna make sure this works as like a memory mask instead of the actual mask thing. Right, so what we're gonna do here is we're gonna have I call create address mask string. Same thing, it will behave similarly, but probably it will be returning some sort of arrays, like a generator function. So for const address of mask number address value, and then we're gonna set the address with this new value. Now the value won't pass through mask, but the address pass through mask, right? And the mask we created using the create address mask instead. Alright, so this part of code we don't have to change anymore. So now we just focus on creating address mask. Same thing goes, we return object with a method called mask, and it takes in address right now. Right, so let's see. We can do the similar thing as well over here. And then let's see. We're gonna return different combination of x's, right? Which means that we need to know when or where is the x, and then probably we will look through all the possible combination of x, and then all possible combination of x, right? Let's see the input. Right there, some of them has actually a lot of x's. But we'll see how it gets. It doesn't seem a lot of x, right? So probably we can actually go through it can probably, so this one is the one that I feel like has the most x's, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the most is like 2 to the power of 9, which is still 512 12 different kind of combinations, which I find it's still not that bad, right? Okay, so what I'm gonna do here is that address, we are going to firstly mask the content first, right? So probably we're gonna copy this thing over here. Similarly, okay, I'm gonna have this over here, and instead of a string, probably we're gonna do it like an array, so that we can actually change the value at any time. I'm gonna make this a generator function, so that we can iterate through the return value. So we can yield different kind of values and we can iterate through them, right? And okay, so while we're looping through, x is actually, so instead of this, we're gonna say this equals to, this is still equals to x, right? Probably we need to record the position of x. Position x position, right? If it's 0, then it's unchanged, which means that binary value I equals to the binary value I. Break. If it's 1, then we are going to use the mask value, which is this, right? Which is 1. Okay. And over here, we're going to record the position of x. So this will be dot push I. Think that's roughly it. And after that, we are going to loop through all the different combination of x, right? So it depends on how many x's we have, right? So we're going to start with 0, and then I less than, if it's 2, then we are going to be 2 to the power of math power 2 to the power of number of x's, right? So that means it's the x position dot length to the power x position of length, and then x I plus plus. Right, so we're gonna loop through all the possible position, and over here, for each of the number, okay, so we're gonna have j again, which is the bit position. Okay, we're gonna have a bit position goes to 0, and bit position less than x position dot length. Okay, so the first loop is that we're going to loop through all the possible combinations, right? So if it's 2 x's, then we are going to go from 0, 1, 2, 3, right? 0 to all the way to 4 minus 1, right? And then over here, we are actually going through, for example, for each number, we're going to go through different bit position. So we're going to go, for example, because we have 4 different combinations, 2 different x's, then we're going to go for x at 0 position, x at 1 position, right? So over here, so x position dot bit position will be the okay, this should be the index, so name it index better. So the bit position index, so bit position, so this, so we're gonna set the result binary value of bit position equals to something, right? And this something, it actually depends on the I, right? Depends on the I, and actually depends on the value of I at the current bit position. Right, so it's 1 bit position index. So if it's 1 at that position, then we're going to be setting 1. With 0, then we're going to set it at 0. Okay. And once we set it over here, once we loop through, probably gonna yield this value, which is result binary value dot join. And we're gonna make it like a number, so we're gonna be parse int with 2. Right, so we're gonna yield this thing over here. So let's try to run this again. So okay, so this is no longer value, but this is address. And result binary value is not. Result binary value. Okay, this should be I. Okay, you get a new number. I'm gonna try it over here. And let's submit. Yes, that's the right answer. And yeah, so we try to go through all different possible position, all possible combinations of the address, and we return that, right? So a high level understanding of this is that we probably have two x's and maybe position 1. So probably we have like x100x. Then we have two position of x's, which is position at bit 1, and so this is 1 and this is like 1, 2, 3, 4, 5. Right? So we have an array of x and 1. And 0. What we're going to do over here, this loop is actually looping through value. So 2 x's, then we can actually loop through 0, 1, 2, and 3. And for each of them in binary, they are actually 0, 0, 0, 1, 1, 0, and 1, 1. Right? So we're going to loop through all this. And then for each of the bits, right? So there's 2 bits, just nice, there's 2x. And that's actually how it is correlates, because we are going to loop through as 2 to the power of that number of x's, right? So if we have 3 x's, we're going to loop through number 8. Then we actually go from 0, 0, 0 all the way to 1, 1, 1, which is 3 bits, right? And for each of the bits, we're going to find whether this bit is value 0 or this bit or 1, and this bit is value 0 and 1, and then we're going to replace it. So we're going to, by replacing, what it means is that we're going to replace it as this as 0, this as 0, this as 1, this as 0, and then this as 1, this as 0, and this as 1, this as 1, right? So once we replace them, what we do next is that actually we're going to join it and then parse it as number, right? So this will lead us to 0, 1, 0, 0, 0, 1, 0, 1, and then 1, 1, 0, 0, 0, and 1, 1, 0, 0, 1, right? And then all of this, we'll get the decimal version of it, and then we are going to yield it, right? So we yield 4 times, and over here we can iterate through. So this is like writing an iterator using a generator pattern, right? We loop through and then we set value of the address, and that's all, right? So that is day 14, and we are done. And if you like what I've done so far, please give me a thumbs up and comment down below if you think there's anything that I can improve on. And that's all for now. If you want to watch day 15, please remember to subscribe on my channel so that you know when it's coming out. So subscribe button probably will be around here. Okay? See ya!